Hello. Yeah. Okay. Hi. So let's start the session. Okay. So I will be teaching assignment 12, week 12, previous year's question paper for assignment 12. And let's start the session. All right. Okay. Okay. So, so the first question here is antenna located in a city is a source of radio waves. The time does it take the wave to reach the town 12,000 kilometers away from the city in milliseconds. So, okay, so antenna is located in a city and is a source of radio waves. Okay, yeah, ठीक है. Then it's asked that time kitna how much time it will take to reach a distance of 12,000 kilometers. Okay, so Gokul, can you tell me how to solve this question? What will be the speed of these waves? No? Okay, all right. So see, for the medium, if the medium is air, then it's the radio waves will be traveling with the speed of light. So their speed will be c, which is 3 into 10 to the power 8 milliseconds, right? 3 into 10 to the power 8 milli, sorry, meter per second square per second. Yeah. So speed of light will be 3 into 10 to the power 8 meter per second. So let's see how to solve this question. So we know the distance, which is 12,000 kilometers, and we know the speed of the wave, which is 3 into 10 to the power 8 meter per second. So time will be distance upon speed, and we will solve it, and we get 40 milliseconds. Right? How much we got the time? 40 milliseconds. So here the answer will be 40 milliseconds, right? So time t is 40 milliseconds. ठीक है? Got it right? You have any doubt here, Gokul?
No, ma'am. No, ma'am.
Okay, let's go. So the second question is the radiation resistance of half wave dipole is in ohms. Okay, so you have to find which kind of antenna for a half wave dipole. All right, and it should be in ohms. The unit should be in ohms. So can you tell me how to, like, what will be the answer, Gokul?
Sound degree.
Yes, yes, very good. So 73 ohms is the radiation resistance of half wave dipole. Okay, so let's go for the third question. In normal dispersion region, d omega by d beta is greater than 0, d omega by d beta is less than 0, or d omega by d beta is 0, none of these. So what will be the condition for normal dispersion region? So can you tell me what will be the normal dispersion region? What will be the relationship for d omega by d beta? Try. Okay, so here group velocity will be greater than 0, which means that d omega by d beta will be greater than 0. So for a normal dispersion region, d omega by d beta will be greater than 0. Why? Because our group velocity Vg will be greater than 0. Okay, any doubts?
No, ma'am. No, ma'am.
Okay, chalo, let's go ahead for question number 4. Okay, a very small thin wire of length lambda by 100 has a radiation resistance of. Okay, so small thin wire is given, length is given, lambda by 100 is equals to L is equals to lambda by 100. Okay, has a radiation resistance. Again, radiation resistance has asked, and for a small thin wire. So, how to solve this question? Gokul, do you know the formula for this question? What we will be applying?
Sorry, ma'am. I don't know, ma'am.
Okay, okay, no problem. Okay, so the radiation resistance of short thin wire of length lambda by 100 is, so this is the formula. Radiation for radiation resistance of a short thin wire is given as 80 pi square L by lambda whole square. Okay, so we know 80 pi square and we know L by lambda. Here L by lambda is, here L is equals to lambda by 100, right? So L by lambda will be how much? 100, which is equals to 10 to the power minus 2, right? Yeah. So we will put 10 to the power minus 2 here and square it. So when we square the 10 power minus 2, so here first radiation resistance is equals to R rad is equals to 80 pi square L by lambda, right? Which is equals to 80 pi square, and 10 to the power minus 2 square is equals to 10 to the power minus 4, right? So this. So yeah. So R rad will be how much? 0.07. Okay. So here we will put, no. Here we will put 0.07. 0.07. Any doubt here?
No, ma'am.
Okay. Let's go ahead. Okay. Question number 5. The directivity of half wave dipole. Tell me, what is half wave dipole? There in the question there are so many questions where half wave dipole is asked. What is half wave dipole? Try.
L is equal to lambda by 2, ma'am. That
Yeah.
wavelength is.
Hmm. Yes. So whatever will be the operating frequency, the length of the antenna will be lambda by 2. So that antenna is known as half wave dipole antenna. It is also known as Hertz antenna. What antenna? Hertz. Okay. Now let's go. So the directivity of half wave dipole antenna will be, okay. So directivity of half wave dipole is 1.64. But this 1.64 is in absolute terms. Okay, so we have to convert, since in the question it's asked in dB, right? All the options are given in dB. So what we will do is we will convert the 1.64, the absolute term, into dB, which will be equals to 2.15 dB. Okay, so the directivity of half wave dipole will be in dB will be 2.15.
Ma'am,
Ha.
how to convert dB, ma'am?
How to convert absolute unit into directivity? Is that what you are asking?
Uh,
Okay.
yes, ma'am.
Yeah. So it's a for any value like 1.64. Okay. Directivity will be equals to 10 log base 10 of 1.64. All right. So
Okay, ma'am. Okay, ma'am.
let's see. Let's go ahead and see log base 10 of 1.64 is 0.214. Okay, and then we will multiply this with 10, so we will get 2.148. So approximately what will be the total value, what will be the value? 2.15 dB. Okay, so here 2.15 dB. Got it?
Okay, ma'am.
Okay, so let's go ahead. A magnetic field strength of 5 microamperes per meter is required at a point of on theta is equals to pi by 2. Okay, 2 km from an 2 kilometers from an antenna air. Okay, so a magnetic field strength of 5 microamperes per meter is required at a point on theta is equals to pi by 2 from 2 kilometers from an antenna in air. Okay, neglecting ohmic laws is the power transmitted by Hertzian dipole antenna of length lambda by 25 is. So I just told you what Hertzian mean, right? Hertzian means a half wave dipole antenna. Hertzian dipole antenna of length lambda by 25 is given, and it is this kind of antenna is the power is being transmitted from a Hertzian dipole antenna. Okay, and it is asked that micro ampere per meter is required. Okay, on a from the antenna to 2 kilometers away. uh, no, one second, sorry. Yeah, so the question here says that there is a antenna. Okay, the antenna shape is Hertzian dipole. It has a length of lambda by 25. Okay, now it's asked that 2 kilometers away from the antenna, if we want a magnetic field strength of 5 microamperes per meter. Okay, this is what we have to get. Then what will be the power transmitted? So power transmitted is asked to us. You understood the question, right? So power transmitted is asked from us. We have been given the antenna type. Antenna type is Hertzian. It has a length of lambda by 25. And what it wants, let's say this is our antenna. Okay, and it is transmitting power. So at a length of 2 kilometers, okay, at a point in air, the magnetic field strength is how much? It is 5 microamperes per meter. So what will be the power transmitted? So power transmitted is asked to us. Okay, got the question? The gist of the question, you got it, right?
Ma'am,
Hmm.
half I naught rate square, ma'am.
What?
Half I naught square into R radian, the formula. Power
Yeah.
transmitted.
Ha. Okay. Okay. Let's go and see. Yes. So first thing is, it is given to us h phi s. The magnitude of h phi s is given to us, and for Hertzian dipole antenna we know that h phi s is, magnitude of h phi s is how much? I naught beta dl sine theta upon 4 pi r. Now theta is given to us, r is given to us. R is how much? Go ahead.
2, ma'am, 2.
Yes, 2 kilometers. That is 2 into 10 to the power 3. Yeah. And dl is given to us, which is equals to lambda by 25. Then beta dl will be how much? Beta is 2 pi by lambda, right? We'll put it here. So beta dl will be 2 pi by lambda into lambda by 25. So this will be 2 pi by 25. So we know this, which is 5 micro, how much it was? 5 micro amperes per meter. Yeah. So 5 micro, which is 5 into 10 to the power minus 6. We know, we don't know the I naught, but we know the other things. We know beta dl, we know sine theta. Put sine, put theta is equals to pi by 2, which will become, sine theta will become 1, right? So this will be 1. Huh. So I naught into 25 by 2 pi by 25, and 2 pi r we know. So we got, from here we got the value of I naught, right? Which is equals to 0.5 amperes. Now we will put it in the formula for power transmitted or power radiated basically. So power radiated will be 40 pi square TL by lambda square, which is lambda by L, L by lambda square I naught. So we know the value of I naught, we know the value of L by lambda, we know the value of 40 pi square. So which will be, we will put all the values here. When we got P transmitted or radiated equals to 158 milliwatts, right? Any doubt here? So 158 milliwatts. Any doubt here?
Ma'am,
Hmm.
I not fine, ma'am. I not, we use another formula, ma'am. 10 divided by 10 pi square into lambda by rho naught whole square.
What? Um, you are,
First we find I naught.
yes, yes.
Yes,
And
ma'am.
how you are going to find out I naught?
Another formula, ma'am.
Yeah, go ahead, tell me.
10 divided by 10 pi square into 10 divided by 10 pi square into lambda by rho square into 10 power minus 3, ma'am.
Rho square, lambda by rho square
Yes, ma'am.
into.
Into 10 power minus 3.
So from where you are getting this value?
Ma'am, rho means density. Oh, okay, ma'am. Okay.
Yeah, so we will be using those terms which we know. So we use the formula where only one term is missing, so that we can find the value. Here h is given to us, magnitude of
Okay,
h
ma'am.
was
Okay, ma'am.
given to us,
Thanks.
right? So that's why. Okay, all right.
Okay,
So
ma'am.
let's go ahead. In question 6, the transmit power in case of half wave dipole. Okay, so now the power transmitted will have uh, different this thing. It will have different, now it will have different I naught, and it will have different power transmitted, since the dipole antenna is changed from Hertz dipole antenna to half wave dipole antenna. Okay, so now for half wave dipole antenna, our magnitude of magnetic field will become I naught cos pi by 2 cos theta 2 pi r sin theta. So now we'll put all the values and find out I naught, right, which will be equals to 20 pi milliamperes. Now the power radiated will be how much? Half I naught square r radiated. So resistance of R we know, right? Radiation resistance we knew already, which is 73 ohms. We'll put the other values and we'll get 144 milliwatts power radiated. Do you have any doubt here?
No, ma'am.
Okay. Okay, next question. So next question here is the electric field intensity at a distance of 10 kilometer from an antenna having a directive gain of 5 dB and radiating a total power of 20 kilowatts. Okay. So electric field intensity is asked to us. E is asked. Okay. Distance D is given to us. D is how much? 10 into 10 to the power 3. Right? D is given to us from an antenna having a directive gain of 5 dB. Okay, so gain is given to us. Let's write it a directive. Let's write it as a D, capital D. Okay, which is 5 dBs, and total radiating power is asked. Radiating power is also given to us. Electric field is asked. Okay, so let's see how to solve this question. So gain in dB is given. First, we will convert the gain in dB into normal absolute value. So, like the way I told you, we'll put 5 dB is equals to 10 log the absolute value of gain. So, gain will become 3.162. You have any doubt till here?
No, ma'am. No, ma'am.
Okay. Okay. Now, the power will be how much? GD into power radiated upon 4 pi square. So, power will become how much? GD pi radiation upon 4 pi r square. Another formula for power transmitted is equals to ES mod ES square upon 2 eta. So we'll put this is equals to this. Okay. Now we know GD, we know radiated power, we know 4 pi r square. We know eta, right? How much eta is here? Please type.
Eta not given, ma'am.
Eta not given, but eta is like eta is a constant, right? So how
Okay,
much?
ma'am. Okay.
It's a free space impedance. So how much is a free space impedance? Is 3,
125, ma'am.
huh? 120 pi.
125.
So 120 pi is how much?
Ma'am, or 377 ohm.
Yes, yes, very
Okay,
good.
ma'am.
So everywhere we read it as, right? We read free space impedance as 377 ohms. So we'll put here 120 pi into GD from we already got GD, right? We know P radiated. Radiated power is given in the question, which is 20 kilowatts. We'll put 20 kilowatts here. 2 pi r square, we know 2 pi value, we know r. Here r is also given, right? Distance is given as 10 into 10 to the power 3. So we will put those values here and we will find out mod ES, volts per meter. 0.1948 volts per meter. You have any doubt here? Have
No,
any?
ma'am.
No. Cool, cool. So we'll write 0.9, 0.19 volts per meter. This is the electric field intensity. The magnitude of electric field intensity. Okay. Magnitude. Okay. Let's go ahead. Question number 9. The maximum effective area of lambda by 2 dipole operating at 30 megahertz. What does lambda by 2 dipole means?
So heads that
Hertz or half wave. So half wave, it's going on. We have so many questions on half wave dipole antenna. So let's see. The maximum effective area of lambda by 2 dipole operating at 30 megahertz is. Okay, so how to solve this question? Go ahead, try to solve this question. How we will solve this question?
PR is equal to E naught square divided by 2 neta into area, ma'am.
Mm-hmm. Effective area. Yeah. Okay. So for effect, the formula for effective area is AE is equals to lambda square upon 4 pi gain in theta and phi. So here lambda is equals to C by F. So first we will find out the lambda. So lambda will be, frequency here is given as 30 megahertz, which is 30 into 10 to the power 6 hertz, right? And we know C, which is 3 into 10 to the power 8. So lambda will be 10 meters. Lambda matlab wavelength. Yeah. So wavelength is, ha. So gain in terms of theta and phi will be eta upon pi r radiated into f square, where f is a function of theta. So we'll put all this. We'll, eta here is 120 pi, which is equals to 377 pi r radiated. R radiated we have already discussed for half wave dipole is how much? 73. So that we put, and f square in theta. So which is equals to 1.64 f square theta. Now we know that gain in dB for sorry, not in gain in absolute term for half wave dipole antenna is 1.64, right? We know that, we have already discussed here. Where have we discussed this? Here, the directivity of half wave dipole antenna, right? So assuming that it has efficiency of 1, we said that the directivity of half wave dipole antenna is equals to gain of half wave dipole antenna, which is equals to 1.64. Now we'll put all these values here in the this formula, lambda upon 4 pi gt. So we got 10 square upon 4 pi into 1.64, which is equals to 13.05 meter square. So this is effective area. So the maximum effective area for a half wave dipole antenna, where it went? Oh, one second. So the maximum effective area for a half wave dipole antenna operating at 30 megahertz will be 13.05 meter square. So can you tell me, uh, first tell me, do you have any doubt in this question? No, right? Okay, let's go ahead. Tell me one thing. What is the effective area and what is the actual area of an antenna? What does that mean? Whatever you can guess, it's no, there is no correct answer, no wrong answer. There is one correct answer, and but since you are trying for the first time and since you are learning, it's okay to be wrong. It's all right. You go ahead, you tell me what you are thinking with
Ma'am,
ha.
effective power means ratio of average power received to the load to the time average power density, ma'am.
No, I'm asking about effective area. In practical terms, what does effective area and what is actual area of one antenna means? This is what I'm asking. Try. Okay, I will tell you. No problem. I will tell you. So, see, the actual area is of an antenna is the physical antenna that physical the total area, physical area of that antenna. Let's say you see one antenna of 10 uh, 10 centimeter. Let's say you are seeing one antenna which has a physical length of 10 centimeter and it has a width of 10 centimeter. So basically it has 100 centimeter area. So this area which is physical, which it is known as actual area of that antenna. Okay, now the effective area means the wave that we are feeding into that antenna, what that wave feels. Okay, this effective area is area which that wave perceives of that antenna. Okay, for all the calculations we use effective area instead of actual area, because there is actual area which is physical, which we can see, but the effective area is what the wave, the electromagnetic wave feels on that antenna. What not feels, what I'm not getting the actual term. The uh, mm, what the actual what the wave go through. Okay, the electromagnetic wave, whatever the area is of the antenna, which wave actually goes through, so that is effective area. And actual antenna, actual area is the physical area of that antenna. Okay, so they are two different. It, this effective area depends on the dielectric of the substrate. Okay, it depends on the frequency of operation. Okay, it changes with the frequency of operation, the dielectric of that substrate where antenna is. Okay, while the actual area does not change, it remains the same. Okay, yeah, let's go ahead. uh, you have any doubt here? This question number
No,
9
ma'am.
is clear, right? Hmm. Okay, let's go ahead. Question number 10. The transmitting and receiving antennas are separated by a distance of 200 lambda. Okay, so there is one transmitting antenna, one receiving antenna. This is transmitting, this is receiving. Okay, the distance is how much? 200 lambdas. Okay, and have a directive gain of 25 and 18 dB. Okay, this one has a gain of 25, this one has a gain of 18. Okay, respectively. If 5 milliwatts of power is to be received, the minimum transmitted power in watts is. So how much, what will be the minimum power transmitted by this antenna so that this antenna receives at least 5 milliwatts? Okay, now how do we solve this question?
Ma'am,
Hmm.
by using Fritz's equation, ma'am.
Yes, yes, very good.
PR,
Yeah.
PR is equal to GDR into GDT into lambda by 4 pi whole square into PT, ma'am.
Yes, very good, very good. Correct, correct. Yeah. So by using Friis equation, we can solve this question. So transmitted gain for the transmitted antenna was 25 dB. So we will convert it into absolute term. This will become 316.23. Similarly, gain for receiving antenna is 18 dB. We will convert it into absolute term. This will become 63.1. Now using Friis equation, PR is equals to GT into lambda upon 4 pi R square whole square into PT. So PT is equals to, we will shift all these terms this side and we will get, shift all these terms this side and we will get PR into 4 pi R upon lambda whole square into 1 upon GRGT. Now we will put all these values and we got PT is equals to 1.583 watts. You have any doubt here? Do you have?
No, ma'am.
Okay, okay, cool. All right, so if you don't have any doubt, then okay, then we will end the session here. and all the best for your last assignment, and I hope that you do well. Okay.
Ma'am,
Yeah, go ahead.
ma'am,
Yeah.
hall ticket when will come, ma'am?
It will be announced on your portal. It will be announced to you, so don't worry, it
Okay,
will
ma'am.
be announced. Okay. Chalo. Bye bye, all the best.
Thank you, ma'am.
Thank you.